In this video, I'm going to use some of the ideal gas concepts to solve an IB question that actually doesn't involve numbers, but rather it involves more ratios and factors. This is the question at hand. Okay, an ideal gas is held in a container that can expand and compress freely. The mass of gas is held constant. By what factor will the volume in the container change if the temperature is halved and pressure is tripled? Now, this is one of those questions that is what I call a two instances problem. You've almost got a initial and final, or you could say like they want to know basically how is the volume changed. So you've almost got like a volume at a second scenario compared to the initial scenario that it started with. How can we come up with this equation? Because this is actually not provided in IB. This one is provided, however, and we can use this to come up with a sort of two instances formula where we want to know, I'm just being lazy there, two instances. We want to know how the volume is going to be affected based on these changes here, temperature and pressure changing by some factor. Well, the answer is actually quite easy, right? This R value, if you're studying this topic, you should know by now that pressure times volume divided by moles times temperature is always going to equal this R value of 8.3 joules per mole Kelvin or Kelvin mole. That is constant. It's always going to be that way if it's an ideal gas, which we're assuming it is in this case. So if this is always going to be the answer, well then it shouldn't matter whether it's instant 1, instant 2, instance 2, instance 3, instance 4. It doesn't matter. This is always going to, I could go on, right? It doesn't matter. It's always going to equal 8.31. But all we do is say that instance 1 should be equal to instance 2. That's all it is. So using this formula that you should be given, you can basically derive this one. And even if you're not given this one, maybe you're not in IB and your teacher has told you you're not going to be given this equation, really this one, once you use it a few times, is not hard to remember. PV equals nRT. So just kind of rearranging, solving for R, the constant value, you will get this, and that's kind of the formula that we're going to need to use here. So I'm going to erase this and just write my two instances formula. So this two instances formula states that you could use initial and final. I'm just going to use 1 and 2. So this is basically just saying you can change whatever you want, but as one thing goes up, the other thing will go down, and they'll kind of balance out. It's still going to be equal to 8.31. So let's think about the three big things that they've given us here. The mass is held constant. That's important. The temperature is halved. That's important. And the pressure is tripled. Those are three very, very important things. And the question we're kind of wondering is, what factor will the volume change? Okay, so what will be the change in volume? First thing is the easy thing, okay? The mass of the gas is held constant. Anytime you have something constant, you can basically just eliminate it. I'm going to go ahead and erase it, actually, make it look even nicer. The reason you can cross that off, just imagine subbing in a value there. If you knew you had 5 moles of gas and it didn't change, well, having a 5 on each side of your equation in the denominator will not change your result. It's almost like algebra. Whatever you do to the left side, you have to do to the right side. So I just basically multiplied each side by n to eliminate the n values. It's kind of what I did there. And I'm allowed to do that because the masses are the same. If the masses were different, you could not do that. So let's look at temperature first. The temperature is halved. All that means is that my second temperature is half of my first temperature. That's going to be very important. So I've just mathematically described that my final temperature, or my second instant, okay, is going to have a temperature that is half of the initial temperature. So maybe it went from 300 Kelvin to 150 Kelvin. You can try that one out. Now let's look at the pressure. The pressure is tripled. Okay, that just means that my new pressure, or the pressure in my second instant, my second scenario, P final, is just triple. You can write it any way you want, as long as you're expressing that mathematically, that it is triple the first pressure. That's it. I have now expressed these kind of two very important changes mathematically, and I'm just going to look at how that affects my V2. How is that going to affect my final volume? So let's get to it. Let's sub these into the equation. You're basically trying to see how many things you can eliminate from this equation to find out the factor that the volume will change. Well, let's just go ahead and pop, instead of P2, I'm going to fire this into my equation. Because I'm allowed, because mathematically this is the same as P2. That's what this equation here means. Then I'm going to do the same thing with this guy. Instead of T2, I'm allowed to replace that with this guy. So now you can see pretty quickly that I have a completely different equation, or it looks completely different. And let's see how we do. So P2 is now actually triple P1, that's what I've subbed in, okay, times V2, divided by, instead of T2, I'm going to write half T1. Here we go. Let's start to simplify this. Pause the video if you haven't copied this down, because I'm just going to erase the right half of my screen here. So taking this, let's simplify this now, okay? I'm saying that P1 times V1 divided by T1 is equal to triple my first pressure times the new volume divided by 1/2 T1, half the first temperature. Okay, just like we crossed out moles earlier, I can cross out anything that is matching on each side of the equation, if they are on the same side of the fraction as well. So be careful on that. This is a numerator and this is a numerator. Same thing with temperature. Okay, if I see that they're both in the denominator, I can eliminate that. And this is sort of my final answer once I touch it up. I'm now left with, and remember there are actually imaginary ones left behind when you cross something out. It's like dividing something by itself. It kind of leaves behind a little 1. But because we're multiplying by 1 does nothing. So I'm left with volume 1 equals 3 times V2 divided by 1/2. Okay, why don't we get rid of that fraction, because it's pretty ugly, right? Dividing by a fraction is like multiplying by the reciprocal, right? Dividing by a fraction is like multiplying by the reciprocal. That's a little bit of fractions tied into this question here. Now, a lot of people make this mistake and think they're done. They might think that it's increased by a factor of 6, but that is not the case. Remember, I'm trying to figure out the new volume. What is the new volume? What is the new volume compared to the initial volume? So be careful. This will actually simplify to V1 equals 6 times V2, but I want to know the new volume. I'm actually solving for the new volume. So the final answer, you can see that the final volume is 1/6 of the initial volume. In this problem, it's asking for what factor the volume is changed. So the multiple choice option would have to only provide you with various factors, and a factor is just like a multiplier. So although I have this answer V2 equals V1 over 6, really the factor is 1 over 6.